Hi everyone, this is a video about stating the nature of a stationary point. So we've already looked at what a stationary point is. That's where a curve has no gradient, and that's usually between where a negative gradient turns into a positive gradient, so a turning point, or sometimes it can actually be between two gradients that are the same as each other. So a positive goes flat and then goes positive again, or perhaps a negative gradient goes flat and then becomes negative again. So that's what we call a point of inflection. I'll show you what I mean. We're stating the nature of a stationary point. So that basically means defining whether a stationary point is a turning point or a point of inflection, and we're proving that mathematically. So we already know that a turning point looks something like this. If we have a curve that hypothetically looks something like that, we've got two turning points in this curve. One of them is here, and the other one is here. So as the positive gradient becomes negative, there is a brief moment here where there is no gradient in that curve. So that's what we call the stationary point, and this particular type of stationary point is a turning point. Likewise, with this one here, it goes from negative gradient back to positive, and for a very brief moment between those two gradient changes is a moment where the gradient is zero. That is also a turning point. A point of inflection looks a little bit different, but we find them the exact same way. A point of inflection would be on a curve that wasn't so curvy, wasn't so rounded. Would look something a little bit more like that. So here again we have a cubic, but this one we have a positive gradient here. We also have a positive gradient here, and between the two there's a very brief moment where there's a gradient of zero again. So that's our stationary point. Only this type of stationary point is called a point of inflection. And that's because it sits between two gradients that are the same as each other. The curve does not actually turn. So that's excellent. We know the shape, we know what a point of inflection is, we know what a turning point is, we know that they are both kinds of stationary points, but how do we actually find them or prove what they are mathematically? This is going to be especially important if you're asked to do this in a tech-free question. Obviously you can't graph it using your calculator in a tech-free question, so it's going to be important to find out and prove mathematically what we're looking at. So let's look at an example. The first example I'm going to show you is a cubic again, and it's f of x equals x cubed plus 3x squared take 4. So as we know, the first step to finding where stationary points are is to find the derivative of the function. So f dash of x is going to be 3x squared using our cheat method plus 6x. So where we have no gradient means that the derivative is 0 at that point. So to find where these points are, we're going to solve for x. And we find that x equals 0 and x equals negative 2. So there are 2 points on this function where the gradient is 0. And that's at where x equals negative 2 and where x equals 0. We haven't quite found our points yet. We do still need to find our y coordinates. Sorry. We're going to find the function of 0. And that's negative 4. We're also going to find the function of negative 2, which is 0. So therefore, there are 2 turning points. Sorry, there are 2 stationary points. We don't yet know that they're turning points, although it's likely. And they're located at 0, negative 4, and negative 2, 0. Alright, so that's the first part of the question done. We found where the stationary points are. We know that there is no gradient at 0, negative 4, and at negative 2, 0. The next part of the question, we actually need to prove what kind of turning points they are, stationary points they are. Again, I keep giving it away, saying that they're turning points because I'm pretty sure that that's what they're going to be, but let's prove it. Okay, there are two ways that we can do this. We can use the function, or we can use the derivative. I'll show you what I mean. Using the function, we can actually just plot a few points of our function to work out what the shape is going to be. So we already know that we've got stationary points at 0, negative 4, down here, and at negative 2, 0, here. Okay, so those are 2 points that I know are on this curve. I just need to find a few more to prove the shape. So I can do that by finding some other coordinates, probably there, there, and there. That makes sense to me, because they're between the points that we already know. So, negative 3. What's the next one? We've got negative 1. And I chose 1. Okay, so here are some more points that I can plot. I've got negative 3, negative 4, I've got negative 1, negative 2, and I've got 1, 0. Let's see what happens when I add these. Negative 3, negative 4 is going to go here. Negative 1, negative 2 is going to go here. And then 1, 0 is going to go here. Fantastic. So I can now see that I must have a shape that looks something like this, which proves that those two stationary points are indeed turning points. Using the derivative gives us the same answer, and it's just another way of finding the same thing, really. We can find the derivative at those same 3 points that I chose. So the derivative of negative 3 will give us the gradient at x equals negative 3, and that's 9. That's a positive number. The gradient at negative 1 is a negative number. It's negative 3. And the gradient at 1 is 9 again, which is again a positive number. So here, the number itself is not as important as the sign of the number. This shows us that we have a positive gradient in that section, a negative gradient in that section, and a positive gradient in that section. So that means I've got positive here, negative here, positive here, and the only way that that can fit between my stationary points is if it has that lightning bolt positive cubic shape, and that again proves that we have turning points and not points of inflection. Need for you to use both methods. You can choose one or the other. I don't mind which one you choose, but you do need to mathematically prove the direction of the curve to be able to prove the shape of that stationary point. The next example I'm going to show you is one that I'm pretty sure is going to be a point of inflection, and its function is f of x equals x cubed, take 6x squared, plus 12x, take 5. Okay, so looking at a function like this, this is a cubic polynomial, so there's 4 terms here. it's difficult looking at that function to be able to imagine what kind of shape it has. If we had an easy one like this, if we had f of x equals x take 5 cubed plus 3, we can see immediately what shape that's going to have. We know that that's going to be a cubic, a positive shape, and that it's going to have one point of inflection, and that's going to be at positive 5, positive 3. But with a polynomial like the one that we've been given, we do need to do a little bit more work to find out what shape it's going to have. The process is exactly the same. Step 1, find your derivative. Step 2, find out what x is when the derivative equals 0. So we're going to end up with this. And I find that I've got an x value of 2. Okay, so what that tells me is that I have one stationary point in this function and that it's at x equals 2. Once again, I need to make sure that I know exactly where it is. It can't just be at x equals 2. It obviously has to have a y coordinate. I plug 2 back into my function. And I find that my y coordinate is going to be 3. So I have a stationary point at 2, 3. Great, so I know it's a stationary point, but I don't know if it's a turning point or a point of inflection. I'm going to guess that it's a point of inflection because there's only one of them, but I do need to prove this mathematically. So let's go ahead. Stating the nature, 1, 2, 3, 4, 5, negative 5, alright, and we know that we have a stationary point at 2, 3, which is right about there. Okay, easy peasy. What I'm going to do is I'm going to choose 2 points either side of my point of inflection. I'm going to choose x equals 1 and x equals 3. I'm going to find out where those points land on the function, and that will tell me exactly what shape I'm going to end up with. So, f of 2 f of 2 we already know. F of 1 is 2, and f of 3 is 4. So that means I've got additional points on my curve at 1, 2, and at 3, 4. So 1, 2 is going to be there, 3, 4 is going to be there, and that proves to me that what I have there, that red spot, is going to be a point of inflection and not a turning point, because it does not turn back on itself. So therefore the stationary point is a point of inflection. And that's how you mathematically prove whether your stationary point is a turning point or a point of inflection. If we have a look in Desmos, I've got our first example, so this was x cubed plus 3x squared take 4, and indeed we have 2 turning points at negative 2, 0 and 0, negative 4, which is exactly what we expected. And our second example, x cubed take 6x squared plus 12x take 5, has a point of inflection at 2, 3, which is again exactly what we found mathematically. If you have any questions.